All right, so let's go ahead and get started. So today we're going to be continuing with capacitance, and then we're going to start talking about magnetism. So the first question that we have for today is actually one of the ones that we didn't quite get to last time, and this involves finding equivalent capacitance. So go ahead and take some time to try to find what the equivalent capacitance of this system is, given all of these capacitors and given their values. One of my graduate professors said something that I think still rings true today, and that's that arithmetic is best done in private, so other people can't see you make mistakes. So hopefully I didn't make any mistakes when I did this, but I'm sure you'll forgive me if I don't know how to add numbers together. So this is the original circuit that we had. What I did was I redrew it a little bit just to make it a little easier to look at. So let's look at what it looked like originally. So this is 60, and then this is 50 going diagonally across, and then we have this 20. Now, the way that this is drawn, it's a little bit difficult to see where things are in series and where they're in parallel because of these two diagonal lines. Now, what I am allowed to do in drawing these is I can move these around as long as where this wire touches the rest of it, it never crosses where another capacitor is. So that means I can take this one and I can reorient it so it's vertical, like this. And that doesn't really change anything, right? The same thing with this one, but this one we have to be a little bit careful of, because like I said, we can move those wires around as long as we don't cross something that's already there. So what I'm going to do is I'm going to take this 60 and I'm going to slide it over to the right so that it's over here. And then the 40 is fine where that is, and now I can take this one and I can rotate it like this. Okay, so now it's a little bit easier to look at. Now the thing that we need to be careful of is, we might think that, okay, well now I have this oriented nicely, I'm just going to add everything in parallel across. Well, we can't quite do that because this system is up here and this system is down here. But what we can do is we can add this in parallel and we can add this in parallel. Okay, so when we do that, what this is going to look like, our rules for adding things in parallel just means that we add the values together directly. And so this has this 12 up here still. This one right here becomes 120. This is still our 50. This is going across here. This is 60. And now I'm also going to add these ones in parallel, and so that makes this a 60, right? Because it's 10 plus 30 plus 20, so that's 60. So this is the next step that we have. Now the next thing that I can do is I realize, am I missing something? No, it's fine. It's fine. So now what I realize is that these two are in series. So what I can do is I can add these together with this rule, and that says that 1 over 60 plus 1 over 60 is equal to REQ here, or CEQ here if I invert this. So this is 2 divided by 60 inverse, which is equal to 30. And so the next one that I have looks like this. So this is 12, this is 120, this is 50, and then this is 30. So 50 and 30. Now the next thing that I can do is I can add these together in parallel. So again, we just add these two values together directly, and so this is going to be 12. Did I lose something here? I did. There's a 12 here. There's a 12 here, sorry. I thought something was looking a little funny. Okay. I mean, you guys can shout out and say, hey, you missed something if I left something off. Okay. So now I can add these two in parallel, which means the circuit is going to look like this now. So this is 120. This is 80. This is 12. Like this. Okay. So then the next thing is to add these two together in series. So I'm going to get something that looks like this. This is 12. This is going to be a value. This is 12. This is 120. 1 over 120 plus 1 over 80, which is going to give me 2 over. This is, I think this is 2 over 220, 240, plus 3 over 240, which is 5 over 240. And then invert this. So this is 240 divided by 5. 240 divided by 5 is 48. Okay. So then we add these in series. So when we add these in series, or sorry, in parallel, this ends up being 60, right? So this is going to be 12 and then 60. I think I did make a mistake here when I added this one. And then add these in parallel, and so this is 1 over 12 plus 1 over 60. So this is 5 over 60. No, I didn't make a mistake. This is 5 over 60. So this is 6 over 60 inverse. And so this is equal to CQ is equal to 10. Okay. Okay. Any questions about this? Yeah. Can you speak up? I can't hear you.
You can't hear me? Okay.
Yeah. Go ahead.
I mean, like, can we just redraw the whole thing as one picture instead of separate them? Because that's so easier to, like, it's very easy for us to lost.
Well, yeah, so ultimately the goal is just to have it as one picture, right?
Yeah, yeah.
So what do you mean when you mean like don't go from...
Yeah, draw it.
Draw what?
Like the picture I drew. I drew.
What was the picture that you draw?
Well, I don't have to, that's fine.
Okay, so the whole idea of drawing it, because I mean, in a way, if you just start here and you say, okay, well, I add this in parallel, I know what that is, and then I know I add it in series, and then I know that I could add this in parallel. You don't necessarily have to redraw the picture at every step, but it's meant to help you to think about what it is that you're doing as you're collapsing the system.
That's what I mean.
So I'm not sure, can you ask the question again? I don't know if I understand.
I don't really have a question. It's just some of my thoughts. I just think it would be easier instead of separate every single step, just draw the whole thing. And it would be easier to understand instead of like every time we calculate something and we...
Oh, so you're saying redraw the picture every time before you do any calculations and then do the calculations after you've redrawn everything?
No, just draw one picture and we can calculate according to that one picture.
She's saying instead of redrawing it multiple times, just take that and then go directly to the end.
Yeah.
And then write out all the like equations. So you don't have to draw multiple pictures, you just draw one of them.
I'm still not sure if I understand. You mean like if I had this picture and then I collapse this, I erase it. I erase it and then label it again on the same picture rather than redrawing it?
You take that whole thing and then you draw another picture, but it's just with more.
It's just with one. Oh, well, I mean, that's where I'm going, and what I'm doing is I'm drawing all the pictures in between, but yeah. So the picture at the end is always just going to be this, right? Is this what you mean, drawing the end? That's where we went. I just drew everything in between to show you how you went from this picture to this picture at the end. But it's not not something that you can just say, okay, well, I'm going to go from here to there. There's a lot of steps in between in order to understand how it is I went from this picture to this picture. Does that clarify things more? Yes. Okay. All right, so let's move on to the next one. So the next one's a little bit simpler, but we want to calculate some different things here. So for this one, again, we want to find what the equivalent capacitance is. Now that we did the first one, this should be pretty easy to do. And then once we do that, we can find what the charge and the voltage is on each one of these capacitors. So to find what the equivalent capacitance is here, the first thing that you need to do is you need to add this one and this one together in parallel. So when you do that, you end up getting something that says the equivalent capacitance of this is going to be 60 microfarads. Then that is in series with this one, and to add those in series, I do 1 over 60 plus 1 over 30 microfarads to the negative 1. So this 1 over 30 is really 2 over 60. Okay, so then I add those together, I get 3 over 60 inverted, which ends up being 20 microfarads. Okay? All right, so then once we have that effectively reduces this system to just this system. Okay, so this is 20 microfarads. Now we can find what the charge is on this capacitor, which is going to be the same charge that's on this one. So the way that you can think about this is when charges split, it's kind of the same way that current splits for resistors. So if I had a system where these were all resistors instead, I could find what the equivalent resistance is to find what the current is coming out, and then that current is going to go, all of it is going to go through this resistor here, right, if this was a resistor system. And the same thing is going to happen with our capacitor system. So if we can find what the equivalent capacitance is, we can find what the charge is on the equivalent capacitor, and then this one doesn't share any of the charge. All the charge goes here. And so when we use Q is equal to VC, what we end up finding is that this is going to be equal to 240 microcoulombs. So this is going to be the charge on Q1, or on capacitor 1. So this is 240 microcoulombs. So then the next thing that we ask is we want to find what the voltage is across C1. And so in order to do that, what we say is Q1 is equal to V1 C1, and then V1 is going to be equal to Q1 divided by C1, which says that this is 240 microcoulombs divided by the capacitance of C1. So this is 30 microfarads, and so this is going to be equal to 8 volts. 8 volts. Okay. So then the next thing that we ask is what is the voltage across C2, which is also the voltage across C3. So the way that we can think about this is if we drew some loop here, and ask ourselves what are the contributions to the potential. This is a potential increase, so this is going to be 12 volts. This is going to be a potential decrease, and we know that that's 8 volts. And then this is going to be another potential decrease, which is an unknown, we'll call V2, and that's equal to 0, right? So we can solve for V2, and what that says is V2, which is also equal to V3, is equal to 4 volts. Okay. Why is it I can say that the voltage across V3 is the same as the voltage across V2? Yeah.
Because they're in parallel.
Yeah, because they're in parallel with each other. So if I go around this path on the inside here, I have to lose that same amount of voltage as I would have to go across this one. Right. Another way that we could show that is if I draw this loop here, right? Whatever voltage I lose here, I have to increase here because the change in voltage around any closed loop is going to be 0. Okay, so there's a couple of ways that we can show that. So then the next part, we wanted to find what the charge on C2 and C3 were. And now that we know the voltage, this is fairly straightforward. So we can say that Q2 is going to be equal to 4 volts times the capacitance here, which is 20 microfarads. And so this is going to be equal to 80 microcoulombs. And Q3 is going to be equal to the same 4 volts times the capacitance C3, which is 40 microfarads. And so this is equal to 160 microcoulombs. Okay? And that's it. Any questions about this one? Okay. And now for something completely different, I'm going to move into magnetism. So I'd like you guys to make a prediction here. So if I have, and I'll show you the actual apparatus that we'll use for this. I have a aluminum pole here that's hollow on the inside, okay? And I have a magnet that has the proper radius so that'll fit in here. And what I want you guys to do is to guess or try to figure out, if I drop this magnet and it takes me about half a second to fall this distance, if I put it in the tube with the north side going down, is it going to be faster, slower, or is there going to be no difference? So this is the first learning catalytics question, so go ahead and start that up and then make a prediction of what you think is going to happen, then we'll see. So let's guess at what this will be. I'm not going to tell you the answer. I'm going to change the question and we're going to do the experiment. But what were some of the reasons that we came up with? What could be the right answer here? A. So some people say, hey, maybe it takes less time. So that could be why. What could make it take less time? Well, I think a natural thing to think is, the Earth has a magnetic field, right? It might be attracted, right? Well, that would be regardless of if it was in the tube or not, I guess. But that could be the right answer. It could be no noticeable difference. It could be more than 5.5 seconds, but we'll see. So now I want you to think about what's going to happen if I flip it. So what do we think is going to happen if I flip it over and I have the south side? Is it going to take longer or shorter? This is going to be the same. So I'll let you guys keep putting the answers in, but let's actually go ahead and test this. So I have my tube here and I have my magnet. This is the north side, so I'm going to put this in here and go really quickly down here. And it takes longer. It takes longer than just dropping. All right, let's see what happens if I put the south side in. Nope, it still takes a long time. Okay.
Friction.
Well, friction could contribute to it, but that's actually not the reason why. Because if we made a wooden tube, it would still fall quickly. So we'll see why this is. I have a video that talks about magnetic levitation, and then it also talks about this phenomena.
It consists of 4 motors connected up to these spinning magnet arrays, and if you spin fast enough, it will actually levitate. That's correct. Let's see if we can do it.
Are you ready? Let's fire it up.
It's lifting. Okay, it's flying now. Is it? Yeah, definitely. Now it is so easy to just move around. That's amazing. Give it a push, like it's got some real. Wow. It can carry some weight, hey? Yeah. That is amazing.
So how does it work? Well, it's similar to how a magnet falling through a pipe is slowed down. Anytime a conductor experiences a changing magnetic field, electric currents are induced in it, which create a magnetic field to oppose that change. And in this case, the spinning magnets induce currents in the copper sheet. they create a magnetic field which is nearly a mirror image of the spinning magnets, and so they're repelled. If the rotors spin fast enough, this repulsion leads to levitation.
That is awesome.
So that's the same way.
Yep.
It's just going to come gently land.
The induced currents then encounter resistance in the copper, so they dissipate their energy as heat.
Whoa. And this copper is pretty hot.
It's gotten warmer. Yeah, I can still keep my hand on it.
Yeah.
For a second or two.
But it is like a hot
Now, have you ever seen induction burners?
Experienced this before.
That's actually the same way that they work.
Except with this one, the changing magnetic field was created by an electromagnet in the base, inducing currents in a light aluminum plate, which levitated.
Whoa!
The plate got so hot, you could boil water on it.
Check out how hot this plate is. If you have two north magnets facing each other, they normally just kind of like fall off.
Yeah.
Is there a similar problem here or no?
Not really, no. And the reason is the magnetic fields that are induced by currents in the copper sheet are a mirror image of the supplied magnetic field, and the effect is so quick that as it moves, it just kind of follows it around.
Making this device work in practice is harder than it looks. For one thing, the magnetic field of the permanent magnets has to be very strong. Neodymium magnets are strong, but there's a special configuration you can use to make them even stronger.
It's called a Hall-Barth array. They're used in particle accelerators. They're used in fridge magnets, actually. Hall-Barth arrays, so they're stronger on the side and keeps the fridge. So use that material overall.
Magnetic field lines run from north to south, and they're normally symmetric on both sides of a magnet. But if you rearrange them like this, the magnetic field lines are channeled almost entirely into one side of the magnetic array, and they cancel out on the other side. This configuration produces a much stronger magnetic field without changing the properties of the magnets. In these rotors, there are 12 wedge-shaped magnets. Their magnetic poles are fixed in this particular arrangement. This increases the magnetic field on the bottom side and almost eliminates it on the top. As the magnets spin, they create a rotating magnetic field in the copper beneath them. This induces currents that create magnetic fields, which oppose the magnetic field of the spinning magnets above. The result is a repulsive force that is effectively lift for this quadcopter. But in addition to lift, there is also drag. Energy is clearly being dissipated in the system as the heat produced by the induced currents in the copper. Net energy comes from the fact the magnetic field of the induced currents is not a perfect mirror of the spinning magnets above. Instead, the induced magnetic poles are slightly ahead. So they produce a backward force on the rotors, which is really a backwards torque. And that's why the rotors on alternate corners have to spin in opposite directions. Because otherwise they would produce a net spin and turn the whole machine in one direction. This way, they cancel out. This principle has been used to achieve levitation in everything from maglev trains to hoverboards. And it's being considered as a means to make the Hyperloop, a superfast system for transporting people and goods through tubes at very low pressure. But instead of spinning the magnets, the vehicle's motion itself would cause the magnetic field to change in the conductive track below.
So in the future, do you think this is going to be how we travel?
I think like ongoing developments in digital motor controllers and very powerful magnets will mean that talking about moving humans and cargo at extremely high speeds is actually something that we can, as a species, kind of look at. Wow, it turns out that getting from one city to another city in the same day is something that the next billion or 2 billion people might have the opportunity to do in one lifetime.
All right.
How much does this thing weigh?
Okay, so as I said, magnets have a lot of industrial applications, and some of the cool ones are the maglev trains, the Large Hadron Collider. If you're familiar with particle physics at all, is a collider in Geneva, Switzerland, that collides protons together, and they use very strong magnets in order to accelerate those. This is also something that you'll find in superconductivity theory. There's the levitating frog experiment. Electric guitars work via magnetic induction. The cell phones that we all use radiate and receive electromagnetic radiation. The generator that you might have at your parents' house that runs on gasoline, or any power plant that's not solar all work by having magnets with changing magnetic fields induce electricity. And then also there's some popular culture references. My roommate thought Batman could beat Magneto in a fight, and he's clearly wrong. Okay, so when we want to talk about magnetic fields, we also want to be able to talk about what they'll do to charges. Now, we already talked about what electric fields do to charges in terms of the force that they apply on them. This force that I have written up here is what's called the Lorentz Force Law. We've talked about the first half of it so far. That's just to say that the electric force is equal to the charge in the presence of electric field times the electric field. But we also have the magnetic portion, which says that if I have some moving particle with some charge Q, then the force on that charge due to the magnetic field is going to be equal to QV cross B. Okay, so this one's a little bit more complicated to understand what the direction the force actually points, because with the electric field it was easy. The force always points in the same direction as the electric field points, or opposite if the charge is negative. But the magnetic field is always going to be mutually perpendicular to the force and the direction the charge is moving. So we're going to get a lot more practice with understanding how we can find what the force is on a charged particle in the presence of a magnetic field. So I have a really short story based on this equation that I tell every time that I teach this topic. So when I was at Texas A&M, there was another graduate student that liked to try to get answers from other people for homework. So we'd go around and say, like, oh, I did this problem, can you check my answers or something. Now his research was based on the magnets that you would have in a particle accelerator. So it's really important for him to understand how this equation works, the Lorentz Force Law. Now he got to his master's defense and his advisor asked him that question. I have a charged particle moving in a magnetic field that has a certain velocity. What's the direction of the force? And he didn't know the answer. So two things to take away from that. One, don't try to cheat off of other people for your homework, because then you'll embarrass yourself when you're in a master's defense. And the other, that at the end of the day you'll know something more than somebody that graduated from Texas A&M with a master's degree in physics. Okay. All right. So we have these different configurations here that are showing magnetic field lines. Now, before I even do this, I want to show you one other thing. So when we talked about electric fields, if we had some dipole like this, we knew that the electric field lines radiated away from the positive charge and went towards the negative charge like this. Now, if we have a bar magnet and we wanted to draw what the magnetic field lines look like, if this is the north side and this is the south side, these magnetic field lines look almost exactly the same. So they'll go from north to south, like this. Let's put another short one in there, like that. Okay. So knowing that the field lines are going to look like that for north and south, and knowing how two north poles interact, two south poles, and a north and a south pole interact, look at these diagrams for these field lines and then try to figure out whether these magnets in set 1 and set 2 are attracted or repelled from each other. Okay, so let's go ahead and talk about this one. So based off of the diagram that I drew on the board, we know that magnetic field lines leave the north side of a magnet and then go towards the south side of the magnet. Now, if I look at these diagrams, I can figure out which side of the magnet I have here. So for this top one in the top left, what's on the left side? What's this side? That's a south side, so that's a north side. And then this is also south side and north side. So north, south, these will be attracted to each other. And then this one, what do I have here? That's a north side, right? And then this is also a north side, so those are going to repel each other. So the answer should be B. Now let's jump into some of these Lorentz Force Law calculations. So I need a little bit of a setup to explain this. So when, in general, if I have two vectors, so just the same way I have two vectors here for the Lorentz Force Law, F vector is equal to Q V cross B. So I have two vectors that have a cross product between them, and I could draw what something like this might look like. So if this is some vector A and this is some vector B, and I say the vector C is equal to A cross B, we want to figure out what the direction that C points. Now, in order to do this, what we do is we take our right hand, this is what's called the right hand rule. We take our right hand and we point our fingers in the direction of A, and then we curl them towards the direction of B, and then our thumb points in the direction that C points. Okay? So if this was like this equation here, if instead of having A, B, and C, if I had the velocity, let's make it a little bit different. We have the velocity and then the magnetic field, and I wanted to find what the direction of the force is. I take my fingers of my right hand, point them in the direction of V, so that points it this way, and then I curl them in the direction of B, and then my thumb points in the direction of the force. So if this was a charged particle with a velocity v like this, and the magnetic field was pointing this way, then the force would be pointing into the board. And the way that we indicate into the board and out of the board is to consider what an arrow looks like. So if we have some arrow, so if I fire this arrow towards the wall, then what I see are the feathers. So if something's moving away from me or going into the board, I'm going to see the feathers. So this is in. And if somebody shoots an arrow at me, it might be the last thing that I see, but what I will see is the tip of it, right? And that tip is just going to look like this circle, and so this is what we call out. So that's the notation that we use to show what into and out of the page of the board look like. So based off of this discussion of the cross product, what I want you to do is to figure out what the direction of the force is for this this particle in the presence of this magnetic field with some velocity that's moving to the right. So what did we say? What did we say? 80% of you said the same thing. Out of the page. Why? Yeah, I point my right hand in the direction of V, and then I have to rotate it in some way so that I can rotate my fingers into the direction of B. And then when I do that, my thumb is going to point out. Okay, good. See, you guys know more than somebody with a master's degree from Texas A&M. Okay. Now how about this one? Now, be careful, and look at this equation. Who knows? Who knows? Hopefully I do, right? That's why they let me talk to you guys about it. Okay, so what do we think? What do we think? It could be up, right? It could be up, and it would make sense that it's up, right? Because if we point our fingers in the direction of V and then curl into B with our right hand, our thumb points up, right? That makes sense. But look at this. It's a negative charge, which means when I plug a negative charge into this equation, that flips the direction. And so our right-hand rule gives us that the force should be up, but the fact that this is a negative charge means that it's going to go down. Okay? Okay. Okay, so this one's a little bit different, right? I'll give you a little bit more time to talk about it, but now I'm not telling you what the direction you're curling your fingers into. I'm telling you the direction that you have to point your thumb, right? Because I tell you what the direction the force is. So let's talk about this one. So I told you here that the force is going to be pointing into the page and the velocity of this positive charge is going to be pointing straight down. And we want to try to figure out what the direction of the magnetic field is. Right? So I kind of give you the first step of the right-hand rule and the last step. And so we need to figure out what the intermediate step is. And so we know that the force is always going to be the direction that our thumb points. Right? So we can point our thumb in the direction of the force, and then our fingers have to point in the direction initially, before we curl them. They have to point in the direction that the velocity is going. So if I point my thumb in the direction of the force, that's going to be in, right? And then my fingers have to point in the direction of the velocity, which is straight down, right? So then when I curl my fingers, that's going to be to the left. That's the direction of the magnetic field. Okay. Do you want me to say that again?
Yes.
Okay.
Yeah.
Okay. So when I'm using this cross product, this third vector here, the resultant vector from doing the cross product operation, that's the vector that points in the direction of your thumb. Okay, so the force is always the direction of the thumb. The velocity is the direction your fingers point before you curl them, and then the magnetic field is the direction that you're curling your fingers into. Okay, so knowing that F is the direction that the force points, what that means is I can take my right hand and then orient it so that my thumb is pointing in the direction of the force, and that direction is going to be in, right? This is the symbol for M. So everybody take your hand and point it like this so that it's pointing in. Your thumb's pointing in. And now I'm free to rotate this around as long as I keep this thumb pointing in the direction of the force. And then I have to rotate that around until my fingers are pointing the direction that the velocity of this particle is going. So now I have my thumb pointing in the right direction, and I have my fingers pointing in the direction the velocity is going. The last thing that we do in order to find what the direction of the magnetic field is now is to curl my fingers in the direction that I'm allowed to curl them. Right? I can only move them this way, right? And so when I curl them in this direction, they're pointing to the left, this way. Okay? Is that better? Yeah. Okay.
Thank
Okay. Let's do another one. Okay. Now we're putting other things together now, right? So now we have the direction of the force, we have the direction that our fingers are curling, and then we need to figure out what the direction of the velocity is. Now, the other thing that you should be careful of, is the fact that this is a negative charge. This is a negative charge. So some of you have realized that when you have a negative charge, you can use the left-hand rule, and that makes things a little bit easier. I would say be careful if you want to do that, that you're sure always that you're using the right-hand rule for positive charges and always using the left hand for negative charges. I personally prefer to always use the right-hand rule and then use a negative sign to change the direction, which ultimately, at higher levels, it's important that you're always consistent with your choices of definitions, which is kind of why I'm personally a little bit locked into doing it like that. So to do this one, I'll do it with my right hand, and then I'll show you how you might have done it with the left hand. So the first thing that we need to do is take our thumb and point it in the direction of the force, okay? And then once I fix that direction, I can rotate my hand all different directions, but ultimately the direction that it needs to point is the direction such that when I curl my fingers 90 degrees, it points into the board, which with my right hand points to the right. Now, because this is a negative charge, that means that this right needs to be negative, which makes it left. Okay. Now, if I was to do this with my left hand, what I would do is I would say, because I have a negative charge, I can use my left hand. So I point my thumb in the direction of the force. I point my fingers, I have to figure out what direction my fingers point, but they do have to curl into the magnetic field, and the direction that it curls into is like this, which is to the left. And then you don't need to worry about the negative sign. But you see that regardless of which way I do this, when I have my thumb pointing up and then curling into the magnetic field, it'll give me the same answer, because this one gives me another negative sign that gives it the same direction as this. Okay. Any questions about that? Okay, so now we get to have a little bit of fun. We have a demo. Some of you are probably looking what's going on up here and say, like, who brought their dad's old microwave or something here. I mean, to be fair, this TV is a lot older than I am too. So what we want to do with this is try to understand, if I bring a magnet near this, so say I'm bringing the north side of a magnet near this, the way this TV works is it's an electron beam. So what's creating the light is a beam of electrons. So what we want to do is to predict how those electrons might move, or if they move, if I bring a magnet towards it, and to get us thinking about what we need to do there. The first thing that I want you to do is, for this setup where I have this south end, I want you to draw the direction that the charge is moving, and then draw the direction that the magnetic field is from the magnet. And then once we have those two things, we can use the Lorentz Force Law to figure out what the direction of the force is. Okay? So go ahead and take a minute to draw those things, and then we'll actually figure out what the direction of the force is, and then make a prediction about what's going to happen when I bring a magnet close to this. Let's go ahead and draw this, and then we'll be ready to make a prediction. And then in the last couple of minutes of class, I'll show you what happens with this. So we know, what should the direction of the magnetic field be from this? If I know I'm bringing the south side of a magnet over here, it's going to be pointing to the left, right? So B is this way, okay? And then we know that the velocity is going to be going out, right? So whatever's accelerating these electrons is launching them towards the front of the screen here. So we know that V is going to be out, okay? And we know that this is a negative charge. So this is a negative charge. So based off of those things, go ahead and predict what's going to happen when I bring this south side of a magnet close to here. So I have my magnetic field is going to be pointing to the left, right? Your left. And the velocity is going to be pointing straight towards you, right? So if I take my right hand and I put it in the direction of the velocity, and then I curl it into the direction of the magnetic field, this points down, right? But this is a negative charge, so it has to point up. Okay, so let's see if that's actually the case here. So we'll have our trusty magnet, and we'll bring this to the side of the TV, and let's see if this goes up. Yep, there it goes. Now, what do we think is going to happen? This will be the last question for today. What do we think is going to happen if I bring the North Pole towards it? What do we think is going to happen if I bring the North Pole towards it? Go ahead and talk about it. Okay, so it looks like the majority of you guys that are putting it in got it. So this is just introducing a negative sign, right? Because I said that if I put the south side towards this, it's going to make it go up. But really, if I put the north side going towards it, that's changing the direction of the magnetic field, and so that's just going to flip the direction of the force. And so when I put the north side here, it goes down. And if I put it up here, it goes that way and this way. No, this one doesn't work that well. Okay. All right, so that's going to be it for today. I hope you guys have a good weekend, and I'll see you on Tuesday.